So hello, everybody. Thank you so much for joining us for this week's SEDS Online webinar. My name is Chelsea Pedersen, if we haven't gotten to meet yet. And before we get started, we'd like to thank our sponsors, IAS, for allowing us to give all of these resources to you for free, sort of the open access of virtual sedimentology, let's say. So next week, we have something really exciting that's coming up. It's going to be the first SEDS Online student webinar series. And that's going to be where we have 4 different talks from students. And so I'm sharing my screen right now. You can get a little bit more information about what's coming your way. But we'll do this every once in a while. And basically we'll have a topic. So next week's topic is mixed systems. So everybody's presentation will be focused on depositional processes in those mixed systems. So take a look at the website if you want to see more information about this upcoming webinar, as well as everything else that we have available for the SEDS Online community. And so I'm really happy to have our presenters today, Drs. Jillian Apps and Frank Peel from the Bureau of Economic Geology, that I'm sure you just heard a little bit more about in our little chat beforehand. And so just to give you a little bit of background on Jill and Frank, Jill received her MA from Cambridge before attending the University of Liverpool for her PhD. And her current research focuses on clastic sedimentology and deep water turbidites. Frank also attended Cambridge before heading to Imperial College for his master's and Oxford for his PhD. His current work focuses on giant salt bodies. Together, they have really an immense amount of experience with over 60 years in the oil and gas industry, as well as experience in academia as well. And they are co-directors of Appial Geosciences Limited. And today they're going to take us on a virtual field trip to Suffolk, UK to see all about the mud tectonics and sedimentation during the early Pleistocene. And with that, Jill, I will let you share your screen, and I look forward to hearing all about this location.
Thank you, Chelsea. Right, let me just find out where share screen's gone. Right, okay. Well, good afternoon to some and good morning to others. So Frank and I are going to take you to this area of Suffolk, which prior to us getting interested in it had really only been studied for the fossil content of these red sandstones and for the glacial effects of, well, what were interpreted as deformation due to the ice emplacement later in the Pleistocene. However, from a small video clip, it became clear to Frank that actually what we might be dealing with is structures that were not easily explained as cryogenic, and that instead they might actually be an analog for some structures we were looking at in the Gulf of Mexico in the Atwater Fold Belt. And so we ended up spending a few summers, well, and some winters, photographing this section, which is rapidly changing because of erosion on the coast. So Frank and I have spent much of our careers studying mobile substrates and in particular salt. But in Trinidad and the Gulf of Mexico and other places elsewhere, there are certain types of mud that can also be mobile substrates. And the fundamental difference between salt and mud is that salt is viscous. It's a viscous fluid, essentially. And at low stress levels, the deformation rate is very slow. And at high stress levels, the deformation rate can be really quite fast. However, we are still talking deformation rates that span a time period of hundreds of thousands of years, maybe even millions of years for movement. And mud is a very different substance. It's a plastic medium, and it doesn't move at all until it reaches its yield point, and at which point it will fail instantaneously. Mud can lose strength so rapidly that it flows just like water, and an example of that would be up in Rissa in Norway. Back in the 60s?
No, more recently than
more
that.
Recently than that, right? There are videos of these very, very treacherous mud rocks moving incredibly fast. So where we're going to take you is to Bawdsey in Suffolk. And at this point, we would very much like for Stephen to take over the screen sharing and to run the virtual field trip we've put together, which is a video.
We're on the east coast of England in the county of Suffolk in a place called Bawdsey. And behind me you can see a Martello tower, which was a defence tower to protect against possible invasion by the forces of Napoleon during the first decade and second decade of the 1800s. The whole area is full of coastal defences. If you swing round here you can see a Second World War radar station and a Second World War gun emplacement. And somewhere in those marshes there is also a First World War pillbox, a rare thing out here. We've been coming here for over 30 years, but we've never actually found that one. This is known as Suffolk's defended shoreline. But there's one invader against which we are not winning the war, and that is the sea itself. The sea, which looks so calm and so peaceful today, over the course of a storm can eat the cliff away at a metre in a single night, and over the course of a bad winter that cliff has receded over 20 metres. But what is the farmer's loss as he loses his land is the geologist's gain, because what's being exposed there is a fantastic bit of geology. And the process by where it is sliced off in thin slices is like the way that Tim's sandbox models are sliced off. And by returning to the same cliff repeated times, we can gradually build up a 3D picture of what is going on here.
This video is a graphic illustration of the rate of erosion. It was taken by an artist called Bettina Fernay, who set up a camera taking photographs every 15 minutes across one winter. And you can see the rate at which the cliff is eroded. Now, her video is much higher quality than this, but it's half an hour long. So I just extracted pictures every couple of weeks from her video to illustrate the point. You can see in the sea that object is a pillbox that was built as a defence in 1940. When it was built, it was on top of the cliff. As the cliff underneath it has eroded, it's fallen off, it's now upside down and gradually sinking into the mud. So here we have the basic setup of the basin. North Sea Basin, relatively deep water. We are in the relatively shallow end of the basin, but it's still marine. The whole thing is very warm. It was a warm period and subject to occasional thermal maxima of very, very warm weather. The basin is anoxic. In addition to that, there is off to the northwest of Scotland a major volcanic centre, igneous centre, with occasional periods of volcanic ash. So there is an ash component in some of the stratigraphy. We're going to be looking at the outcrop here in East Lane, Bawdsey. Also going to be looking at the implications of this for the civil engineering in the Shard of London. Let's look at a stratigraphic section here from southwest to northeast. And we are here in Bawdsey, and you can see this section is eroded, and we are looking at a sad erosional remnant, not much of the original section left. How did it get like this? Start off with the Paleocene transgression, the Thanetian Thanet sands, no coincidence there, to the south of us, clay to the north, the Harwich member, that's clay. On top of that, with subsidence of the London syncline and deposition of the London clay during the early Eocene. Throughout the Miocene, very gentle regional tilting and uplift, and significant erosion, possibly, well, a few hundred meters. Not that significant, to be honest. And at Bawdsey, it's taken out all but possibly a thin skim of the London clay leaving mostly the Harwich formation underneath. But then at this location, it's a very similar lithology. On top of this, deposition of the Pleistocene Red Crag. That's warm water. It's shelly sandstone. So looking at this in chronostratigraphic sense, at our location, here's the clays, London clay, Lambeth, Harwich, and then a 50 million year gap, at the end of which the Red Crag, shallow marine, tidal, warm water, shelly sand of the earliest Pleistocene, followed by normal Pleistocene glacial sediments. So the big question you have to ask yourself is this. Our clay sat there doing very little for about 50 million years. It's never been deeply buried. It's never been subject to any great tectonism. It's only been very gently eroded. And then for 50 million years doing nothing, and suddenly for a period of about 6 months it goes completely ballistic. After that it freezes up and does nothing again for the last million years or so. How does that work?
So here at this location, we can actually see what the cliff is made of. The lower part, in the shades of grey, is the London Clay Formation. Most of the London Clay Formation is Eocene, but here we're looking at the very basal part, which is probably Upper Paleocene, Phoenician, so about 56 million years old. And this may have been deposited during the Paleocene-Eocene thermal maximum conditions. On top of it, there's an unconformity with significant erosion. The upper part of the London clay has been removed, and there's a 55 million year time gap on that surface. Above the unconformity is Glaciation, that's basal Pleistocene, clastic sediments. Now we think of the Pleistocene as being cold, glacial conditions, but this is actually the earliest Pleistocene, and these are warm water sediments. So warm water shells, warm water shell hash, sandstones deposited in a warm sea in coastal conditions. And on top of the Glaciation there's another unconformity, a 1 million year gap this time between the Pleistocene and the soil on top of it. We can also see that from day one of deposition of the Glacian sands, they caused movement of the shale. So we have this beautiful shale withdrawal basin developed behind me, and the shale moved up, forming shale pillows and diapirs and water escape features that you see erupting through the sand. So what we're looking at here is the contact between the mobilized clay above, the mobile shale of the London clay, and the part that has not been mobilized underneath. Within the mobilized section you see a different color, you see fracturing, you see deformation. The layering is folded and deformed. Beneath it the layering is continuous and horizontal, and there is much less fracturing. It's also a completely different color. The boundary between the mobile shale, the mobilized shale, and the non-mobilized shale is very sharp. At some locations it is a razor cut horizontal line. In other places like here, slightly more diffuse.
So, how long did these mini basins take to form? Well, we're very fortunate here because the sediments that are filling the mud withdrawal basins are tidal. So what you see above the unconformity is a super fine grain material, dark brown, above which we have faucets, and that's cross bedding that is migrating from left to right. And in those faucets you have alternating packages of light coloured, very coarse sand, and then fine grained material which is much darker. And those packets are alternating. So what we're seeing are the spring neap cycles of tidal sediments, a tidal wave that is filling this mud withdrawal basin. That whole sequence takes a matter of months. Spring, neap, spring, neap, spring, neap, in a series of changing tidal cycles that perhaps take a year at most.
So let's look at these bundles in a little more detail. At the point just above my finger here. Tidal crossbeds have a very distinctive structure. Each 4-set increment is half a day of sediment, a coarse-grained layer here, followed by a fine-grained layer, representing half a day of rising tide and falling tide. And the amount of coarse-grained material depends on whether you're in the spring or the neap phase of the tidal cycle. During spring tides, the bedforms migrate the most. During neap phases, they migrate the least. So this package here represents a spring tide package, and this finer grained section represents the neap tide package, and the two together is a bundle. Overall, these packages of spring neap deposition, called bundles, can be counted. One tide every 12 hours and 28 tidal cycles every 14 days, and that is a spring neap cycle. And in this way, we can make a good estimate of the length of time the entire basin fill was deposited. And when we did this, it's less than a year.
So now we come back to our favourite mini basin. We're looking at one of the flanks where the beds are turned up near vertical. So this is like a very small example of a mega flap. What I particularly want you to look at here is the white staining, or the white bleaching rather, through the brown stained sand. And this white is showing us where the fluid escape has happened. And we can see that early fluid escape out of the mud up through the sand has on previous cuts that I'll show you in a moment, you can see that the early escape pipes were rotated as the syncline formed, and then they've been cross-cut by the later steep ones. You can also see fluid escape coming up vertically and then escaping along the beds as the beds are rotated up into vertical. So the beds themselves form the vertical conduits where the beds are vertical. So as we said earlier, the sediments being deposited on here started the mud moving. As Jules explained, we can tell how long it took those sediments to form. A very short space of time. As the sediments were weighting down the mud here, in front of it we were forming a mud mound. Out of the top of that mud mound you can see mud diapirs erupting into the sand. And one of the great things here is we can not only track the movement of the mud, we can track the movement of the fluid that's come out of the mud. Because as the water passed through the Pleistocene sand, it washed out some of the materials within it. And we can see the track of where the water has gone by these bleached white strands passing up through the sand. So we can actually determine the path of the water flow. And to some extent, we can also tell the history of that water flow coming out of the mud, which is pretty unique. And for some reason that we don't understand yet, we can see that the very latest fluid escape features go vertically straight through the section, more or less ignoring the beds and cutting through the earlier bed parallel flow. We don't know why yet.
So what then is the mechanism for all this deformation? Let's look at what's been described before. In the literature, this has been described as being due to glacial processes. The story would be that all this warm water sediment was laid down horizontal and undeformed, and then when the climate cooled, the ice sheets came in, you had freeze-thaw, ice push, and ice-related deformation. So we can look at the sediments themselves and find this is definitely not the case. So in this section here, if you look at the little mini basin up here on the right, let's zoom in on that, you can see within this very clear evidence of wedging of these warm water sediments, indicating that these are growth strata. In other words, this mini basin was growing during the warm period, nothing to do with the glaciation. Here's another section. Actually, it's the same mini basin taken 5 years previously when the cliff was a couple of meters further out. And again, you can see onlap and wedging of the section, demonstrating this is syndepositional tectonics. Let's look at a few other features. This is a very nice example of a fluid escape vent. If you look at this carefully, what you find is that the fluid has bent the sediments up. There may be, some of this may actually be sand volcano. What you see within the core of this fluid escape feature is mostly sand. So it doesn't appear to be a diapir. Here's another fluid escape feature. The stem of it is relatively narrow, but as it came up to the surface, it expanded, and we see the familiar bleaching produced by the water flow. And at the mouth of this feature, an open crater that was filled with slightly younger sediment. The other form of fluid escape that was described a little earlier is vertical movement out from the mud through the sediment, causing with conduits of bleaching. Sometimes the fluid flow appears to be going straight upwards. At other times it appears to be following the beds. It's a complicated story, but one that we may be able to unravel a bit. In this photo, you can see a small mud diapir where this actually has the mud in the core of it. Now, this white material around it is not altered sand. This is actually altered mud. So it appears that the process of water flow and mud flow results in alteration of the mud as well as alteration of the sediment. And to the side of it, there's this sinuous water escape feature in this bleached pathway here. Where is all the water coming from? Clearly coming out of the mud. Do we see any evidence of that? Well, it's hard to detect directly, but we do see what we interpret to be polygonal faulting particularly within the upper part of the mud. We've yet to determine how polygonal it is, but it certainly has the right orientations and the right textures. And this is an indication of overpressure being released by dewatering. So another feature that we can describe, we've been looking here to the left and beyond there where things seem to be relatively sensible. We have relatively competent masses of sand and mud pillows and narrow mud diapirs. But to the right, and that's off to the north, things change. And you can see over here a hint of something different. Let's zoom in on that. So we're looking at this region through here. Let's take another photo from another day, and you can see this perhaps even more clearly. What we're looking at is a mud allochthon. You can see, track the sand over the top, round the front, and underneath. And there's the back of the sand in there. There's a second minor allochthon here and another sand sheet underneath it. What's unique about this that doesn't seem to have any analogue in salt tectonics is that the sand that's been then overridden by the mud behaves itself in a very fluid way, producing these crazy looking sand balls where it looks like the sand is forming teardrops collapsing down into the mud. So in summary, these are our observations from left to right as it happens, from south to north along the beach. We see much of the section dominated by large scale mud withdrawal basins, a couple of meters across, up to about 10 meters across, 2, maybe 3 meters deep, with occasional mud diapirs breaking through them. We don't see the top of the mud diapirs, but I'd interpret that they probably had mud volcanoes coming out at the surface. We do see water escape features coming through these mini basins as well. Underneath, the mud is pale or rusty coloured, as distinct to the very black mud beneath. The pale or rusty mud is also strongly deformed, and the sharp line between the deformed mud and the non-deformed mud is very striking. Further off to the north, the behaviour changes, and we see the allochthonous sheets and encapsulated mini basins or sandballs collapsing down through the mud. So it appears there's a change of behaviour from one side to the other. Here, the relatively competent behaviour, and our interpretation for now is that we're looking at probably plastic flow of the mud, whereas to the north, the much weaker apparent behaviour suggests we may be dealing with fluidized mud. So this change of behaviour that we see at Bawdsey, with initial plastic deformation transforming into fluid flow later, is very nicely demonstrated by this sample of quick clay from Rissa in Norway. At slow strain rates, it's plastic. If you speed up the strain rate by stirring it with a spoon in this case, it changes and becomes liquid with no shear strength at all. Very similar to what we think we're seeing. Now this is where the Rissa failure happened. It's been very well studied. You can see at the bottom a photograph of the slump scar with the material sliding down into the lake, and the deposit very nicely imaged. But the process is unfortunately very common in Norway. Here's another example from 1996 from Fjord. Again, you see the up-dip failure cutting back into the onshore, and you can see the deposit moving down into the water as a debris flow. So while we do think there's some similarity here, in the mechanical behaviour, the mode of failure is really different. In Norway and in Canada, the quick clay failures are definitely landslides. The initial failure is more or less instantaneous. The whole thing propagates at the rate at which the retrogressive failure cuts back into the headwall scarp. And the whole thing takes a matter of hours or less. Definitely a landslide. Bawdsey is definitely not a landslide. The whole thing is driven by sediment. Deformation is powered by the sediment. It can only occur at the rate that the sediment is being deposited. So the whole thing takes a matter of a year or so. But we do see the overall same transition, with higher strain rate going from plastic failure to fluidization. Now, we're not saying that the mineralogical processes are the same as the quick clays in Norway. We're not saying that what's happening on the micro scale is the same, just saying that there seems to be on the large scale a similarity. In fact, we do not know what the process, the mineralogical, the microstructural process, is happening at Bawdsey.
So, I'm going to introduce you now to somebody who's got a great deal of experience in this particular field from the engineering point of view. And you may notice a family resemblance here This is Jeffrey Peel, and Jeff, welcome. How are you?
I'm very well, Frank. How are you?
I'm excellent, thank you very much. So we're obviously both now locked down in our respective homes, but prior to that, you were working, I understand, for the Shard.
Yeah,
Can you tell us something about it?
Yeah, of course. I was a project manager, and the firm that I was working for got the job of project managing the construction of the Shard.
And what is the Shard?
Well, it's a giant skyscraper near London Bridge Station in London, and it's like a shard of glass, basically. It's a big cone-shaped shard of glass.
Yeah. So I've got a video here from the BBC, a 30-second time lapse of the construction of the Shard. So I'm going to share our screens,
Sure.
and then invite you to tell me what is going on here. Okay, here we go. So
yeah, that's the old building, 30, 40-story tower, Suffolk Tower, being demolished, and then there's the excavation of the basement for the Shard. Then the Shard's coming up with the lift core and all the floors, and there it is, the skeleton of the Shard of glass. Yeah, so one building came down, big basement was excavated, and a giant new building was constructed.
brilliant.
And
Okay.
right in the middle of sort of very dense concentration of underground train tunnels, escalator tunnels. The London Bridge Station was built on a series of brick viaducts and arches, and you've got Guy's Hospital opposite, and all kinds of infrastructure.
I understand there was important things actually in the ground as well as under the ground there.
Oh yes, well, you know, as with any urban area, there was a lot of services, and in particular down St Thomas Street, there was a 30-inch cast iron water main that had been there for, I don't know, 100 years or so, and we did have a brief time when we thought that was, you know, in danger of being fractured due to the ground movement.
Okay, so tell me what happens to, this tower was built on the London clay. So what are the things that what was your job? What were you watching out for as you were building?
Yeah, well, one of my roles was to manage the ground movement monitoring, and we had our designers, consultants, produce a report giving us what they thought the ground movement would be. First of all, there'd be rebound of the ground when the old tower block was demolished, and that would have a sort of an effect on all the structures within what we call the zone of influence. And then the basement was excavated, and that would cause further rebound of the ground and sort of uplift. And then with the construction of the new building, the ground went down again. And what we were looking for within the zone of influence, and some very touchy stakeholders, London Underground and Network Rail and the hospital authorities and the Thames Water, was we were looking for movement, differential movement on their assets to see if they were going to fail, or if the railway tracks were going to have differential movement.
So what would have been the consequence if there'd been I imagine the movement could have been quite small, but what might the consequences have been if there had been a little bit of tilting of the track?
Well, the obvious one, of course, is the underground trains move within quite a narrowly constrained tunnel environment, and if you get differential movement across the tracks, then it could put the trains outside the dynamic envelope, and they could come into contact with the sides of the tunnel, which would be very bad.
That would not be a good outcome. So how were you monitoring the movement in the ground around and in these tunnels?
Well, we put in a very expensive and high-tech system that had automatic theodolites surveying a whole series of target points throughout, all the tunnels, all the tracks, and escalator tunnels within the zone of influence, and across the way at Guy's Hospital on the facades of buildings to see how much they were moving or tilting, And
what would have happened if you had seen that critical amount of movement happening?
We were getting alerts, and I was fortunate enough to be on 24-hour calls. So day or night, I was getting texts, and if the limits were exceeded, our strategy was to immediately telephone the work, which was 24-hour, and stop work. So until we could work out a solution, basically. And
okay.
Was.
And what sort of solution might you have attempted?
Well, depending on where the issue was, some sort of ground stabilization, or there's a number of options. One of which is injection grouting, cement grout into the ground beneath the structures to try and sort of jack them back up into place. But that's it's a bit it's unpredictable where the grout's going to go. So it does work, but it's not entirely predictable. So.
Yeah. Okay. Thanks. And obviously the tower got built, and nothing fell over, and the trains still run on time, right?
Well, pretty much, yeah. We got through unscathed. I think the closest we came to having to stop work was for that water main in St Thomas Street, but we managed to get through that as well.
Okay, so this time the London clay didn't bite you.
No.
Okay. Thanks very much, Jeff. Okay.
Great pleasure, Frank.
So we've been able to demonstrate today that mud withdrawal basins initiated, subsided and filled in the early Pleistocene in a very short space of time, approximately a year. And then Jeff Beale explained to us today that at present day, the London clay, which is a slightly younger mud rock with very similar properties to the Bawdsey succession, remains a lithology with a challenging tendency to move when loaded or unloaded quickly. And why is this important to us? Well, in geological terms, we need to bear this in mind when we're looking at mobile substrates, that mud and salt deform at very different rates. Salt deforms slowly with respect to sedimentology and depositional processes, and mud deforms rapidly, in fact, instantaneously in geological time. And why does it matter to us now, here in Suffolk? Well, the east coast of Suffolk is the site of two major engineering projects. Firstly, it's round 3 of the wind farm construction offshore in the southern North Sea. And secondly, the construction of the Sizewell C atomic power station just to the north of us here at Bawdsey. And the engineers' reports for both these projects currently assume a stable substrate. However, the reports reference the existing literature that concluded the deformation seen at Bawdsey is glaciotectonic, primarily caused by freeze-thaw cycles in the near-surface substrate. And therefore, because we're not in periglacial climate now, the assumption is that there will be no problem with this type of deformation at present day. But we've shown today that the mud deformation is not caused by glacial processes. Instead, it appears to be caused by loading, probably cyclical loading and unloading, and unequal loading beneath large sediment bedforms. And these are processes that are all too easy to replicate in the present day, especially in engineering projects. And perhaps it is time to review the substrate stability risk. So thank you for your attention today. We do hope that you get an opportunity to visit these mud withdrawal basins at Bawdsey yourselves. But I would like to mention at this point that Bawdsey is a site of special scientific interest. And if you do visit the outcrops, please do not sample them, despite the fact that the waves are eroding the cliff at an annual rate far faster than we could ever sample. Thank you.
Super, thank you guys so much. That was wonderful, and I feel like we got sort of like a three for two special. I didn't know your relative was going to pop on like that, so very cool. So everybody out there in the audience, you can now start typing your questions into the chat. Yep, so as you just got the message there, just remember to let us know where you're watching from, and then we can get to any of those issues or those questions that you might have for Frank and Jill. And if you guys want to share your screen again.
Well, we will, but first off, I think Frank would like to actually show you this mud.
Okay, so
taken from the foreshore, not from the actual outcrop itself.
So this is the clay that was mobile, and you can see it's a solid lump. It's not, at this time frame, it's not mobile at all. If you take that and reconstitute it back into a clay, it's got this texture. You can see that, and basically it looks like ice cream, and it's plastic. This is plastic, and you can stick your finger in it like ice cream. So this is something like what the substrate would have been at the time of deposition. We've not been able to reconstitute it to the point where it becomes a sensitive clay. But just wanted to give you a feel for what it looks like now and what it may have felt like in the past.
Absolutely, yeah. I'm glad you guys brought some props to the virtual field trip. That's super cool. So thanks so much for sharing that. While we're waiting for questions to pop up in the chat, I have one that I wanted to ask since sort of the beginning of the talk. So yeah, Stephen has one in the chat too, so I know he's also super interested. So I'll just grab mine first really quick. And I was wondering what extent, so you guys talked about how the basin was anoxic during certain times of deposition. And so I'm wondering how anoxia and the associated higher amounts of organics that can be deposited simultaneously, how those can play a role in sort of later movement. Does it give it sort of a more like plastic texture? Does it lend itself higher or more so to later stage movement, or? Yeah,
well, it is a factor. I didn't show you a photograph of that little fault, but the faults in the London clay are known as greasy backs because they are literally slippery, slimy faults, and I think it's the organic matter in there that's contributing. It's not because it's immature from the point of hydrocarbon expulsion. So it is just the organic matter itself that is the lubricant there. Okay. When you go off into the middle of the basin, you may be getting higher level maturity and possibly some hydrocarbon effect there coming out of the clay. But I think it's the effects of the organic material itself.
Absolutely. Okay.
Definitely makes it weaker, definitely tends to localize faults.
I would agree with that.
Okay.
Kerogen has that property for sure.
Perfect. Okay, so I'll get to some of the questions that are now popping up. Stephen wants to know and he's coming from Wales. He wants to know if the fluids coming out of the clay, if you have any idea of the chemistry of those fluids.
Reducing.
No, other than, well, Jill just pointed out, Would you like
No,
to?
well, no, we don't actually, Stephen, but it would make a very interesting study if we were allowed to sample, because you might actually see diagenesis associated with the bleaching. But for sure, they were reducing fluids, which doesn't overly surprise me given what they were coming out of. Right, would you like to add to that?
Yeah, so the sands are very orangey brown color. There's a lot of iron in there, and where it's bleached, it's presumably because the reducing fluids have converted the iron 3 to iron 2, which is soluble, and taken the iron component out of the sand. Beyond that, we don't know. We don't. Yeah, they aren't. The fluid is not coming out now. It hasn't. This particular location, that period of mobility happened 1 million years ago, and it hasn't. It has not recurred since. So we can't sample those fluids because there aren't any. But it would be. The crucial thing is, like we said, Jill said at the end of the presentation, could this happen at present day? Could it happen due to the cyclical loading as you build a nuclear power station, for example? We don't know. So there's a lot of unknowns here.
Absolutely. Yeah, it's so slightly frightening, I guess, to think about that, right?
Yeah.
There's this big big issue that might pop up when you start building those different types of facilities.
Yes, I think the interesting thing is that unconformity, well, as illustrated at the moment, is that these mini basins appear to occur in fields. There are groups of them, and then there's whole areas that do not have that kind of mini basin structure to the base of this particular lower Pleistocene sand. And so quite how that plays into whether the mud rock underneath the areas that do not have those mini basins, whether they could still be prone to deformation is, that's an open question to me.
And so there's no real idea yet of the extent of heterogeneity.
No, but having said which, very interestingly, Tim Good, who's in the audience right now, has actually sent us some suspiciously interesting references that refer to a very similar basal contact that we are seeing here. So it'd be really interesting to follow up on those. I suspect what we still won't understand, though, is the spatial frequency of this, because it's so rarely described.
Something that would be really cool, if anybody out there is interested, is we are only seeing this in the outcrop as it is eroded. In the region behind it, it's presumably there in the subsurface, and I suspect that you could image it with ground penetrating radar. You might be able to pick it up with other tools like that, but I feel that if somebody had the time and the inclination to go in, you could actually probably map out where the next set of withdrawal basins and diapirs should be in the area that has not yet been eroded.
Yeah, that makes sense.
Yeah.
Okay, I'll get to the next question. Catherine Giles has a question for you. Very cool, Frank and Jill. Kate from El Paso here. Is some of the color alteration and the polygonal fractures at the top of the clay related to soil processes?
Good question, and we don't know.
In the polygonal faulting, I would say probably yes. The coloring that is seen associated with the withdrawal basins appears to not relate to the surface processes that even might have been paleo soil horizons. It is something clearly to be aware of, but for example, on the one shown here, share screen, shown in the slide that I had up earlier, they are so clearly associated with the diapiric structure here, but even this one is not apparently a front of soil alteration processes coming down from that paleo-erosion surface there. It is the same color above as it is below, and that would suggest that there's actually something going on in terms of very peculiar fluid escape structure coming from the surface, and they all start at this interface between the mudrock and the sand. Now, of course, that may be the lithology is the fluid flow surface even at present day, but I think the association with the edge of the mini basins and so on would suggest that we're right in interpreting it as a paleo process.
Yeah, I wasn't sure from Kate's question whether she was asking about the change of color in the mud or in the sand. So I'll answer.
Well, I
so
think both, and I thought the polygonal faulting changes are absolutely weathering.
So in the mud, what we see is the top layer is altered, it's different color, and it's deformed. And then there's a sharp line, the stuff beneath it is not altered and not deformed. But there's the question then, is it altered because it was deformed, or did it deform because it was altered? In other words, could that be a weathering front that weakened it, and then it deformed down to the bottom of the weathering front? Or is it the deformation front and everything that's deformed has dewatered and that's changed it?
Sure.
And we don't know. And without being able to sample this, because it's an SSSI, there's an awful lot of remaining questions. So we can just observe. That's all we can do.
Yeah, a little bit of question of what came first, the chicken or the egg?
Yeah.
So Kate did clarify, she was actually looking at the clay/mud rock for soils. Is in one of your photos, it looked soily.
Yeah, I do think there's a huge amount of soil processes that need to be deconvolved from the ancient.
Yeah.
So yes, there is undoubtedly, I mean, even if you look at this, you can definitely see that there's a huge amount of present day changes to the clay. Whoops, I'm not doing very well at keeping it in front of the camera.
And it did have 50 million years
this
of
is the other
exposure to get altered before it then started flowing.
Yeah.
So an awful lot could have happened.
It's a very interesting time gap, that. It's a huge amount of time for it to have just sat there. But that's the thing about, I suppose, plastically deforming. They've got to reach the yield point, and until you do something peculiar like cyclically load them, then they don't actually deform.
Yeah.
It's a long time there.
Yeah. Okay, I'm going to get to our next question from Patrick, coming from Erlangen in Germany. One basic question: can rainwater or groundwater or both be one cause for such deformation in the mud?
Yeah.
For changing the properties.
Yeah.
Yes.
So if this is in Rissa in Norway, that quick lay, the critical factor there was the desalination of the pool water by freshwater flow. So when the pool water is saline, the Rissa clay is stable, but when you substitute saline water for fresh water, it becomes metastable and very sensitive. And it's quite possible that there could be a factor here too, because the London clay is a marine clay. Obviously, the original pool water would have been saline, but during the 50 million years of gentle uplift and exposure, it could have been exposed to fresh meteoric water in that top layer. So because we don't know what the mineralogical processes involved are, we can't say, yes, it is just like Rissa, and in which case the fresh water flow could be the culprit. It's one hypothesis. We haven't been able to study it because we can't sample.
Mm-hmm. Yep. Okay, our next question comes from Rashad from Egypt. They say, excellent presentation. Based on the question of Stephen, I believe no XRF analysis or any XRD on the clay samples or even the sand above has been done. If any, what kind of mineralogy difference do you see between both clays?
No,
Okay.
not that we are aware of. I'm not sure that the difference between the in situ undeformed and the deformed has even been noticed before.
Yeah.
So again, it would require, I presume there are ways of getting permission on sites of special scientific interest. It would require a project to be approved for sampling.
Yeah.
And before we lose anyone, if anyone is interested in why some mud rocks are prone to this and others not, I think there is still a lot of work to be done by sedimentologists on what is referred to as shale tectonics. Because to be quite honest, A, a lot of them aren't shales, as in the purest sense of the word, and B, they do seem to only occur at certain times in the depositional history. And I think Chelsea was onto something about the kerogen content. Everybody talks about hydrocarbon maturation as initiating the properties in the clays which cause mobile shale deformation. But I think it's inherent in the actual mineralogy, the original mineralogy, as Chelsea was implying. And I think those properties are equally important. And that hasn't really been documented, certainly in my experience in the literature, just how special these rocks are. There's one in the Eocene that I'm aware of that causes problems all over the place. There's this one, which is also an Eocene mud rock, but the process occurs in the Pleistocene.
Yeah. So mud of exactly the same age of this is seen to be a anomalously slippery deforming layer in the Western Gulf of Mexico.
Yeah.
And it is exactly the same age as this clay interval we're looking at here.
And there's one that might well be exactly the same age in the Shetlands as well.
Okay. Yeah, I think it sounds like a system that might also sort of benefit from some experimental approaches as well, you know, just having organic rich versus organic lean and things like that.
Yeah.
Okay, so our next question is from Bill, coming from Ottawa. Great talk. The virtual field trip was fabulous. What allows the pore fluid pressure, and especially the fluid pressure gradient, to be sustained for days or weeks, especially if the clay has been liquefied?
Good question. I think we have to guess because we aren't there watching it happen. But if this really is deforming plastically, then it may be that you get a withdrawal basin on top and the clay deforms as when the sediment pushes it above the yield point. It'll then deform, the basin will sink down until it just sinks below the yield point, and it'll restabilize for a few days. Then you put another layer on top and it'll continue moving. So in other words, the movement is maybe slow, and the timing is dictated by the deposition of sediment here. And if the deformation it seems clear to me that it's the deformation that causes the fluid escape. So if we're having a sustained period of deformation over the course of a year or so, then the fluid escape related to that deformation is also going to be sustained over the year or so.
Yeah, I'm going to add something else which may or may not be relevant, but I do think it's important. These are tidal sediments. And I've got a feeling that episodicity may be something going on in there in terms of hysteresis in pore pressure. I mean, there's probably huge amounts of fluids available, but for some reason you are building up, maybe on a cyclical basis, an overpressure that is sufficient to change the plasticity response of the mudrocks. So perhaps Frank might like to add to that, but I think it's quite important that there is this cyclical pounding because of the way tidal waves operate, tidal energy operates.
Yeah, so you may get a diurnal loading by the water on top that may be a factor in destabilizing the mud, but also potentially storm waves may be also
That too.
Contributing.
Yeah, Kate also adds into the chat regarding this comment, questioning tidal pumping. So I think
that exactly, Kate. And we shouldn't skip over Tim's question because
no, that was just related to what we were chatting about.
Yeah,
So
absolutely right. I agree, Kate. I agree entirely.
So Tim had 2 comments, and Tim Good is coming from the UK. And his first comment is that the BGS has mapped unusual depressions in the top of the London clay around London, but says little about the genetics of the formation.
We really appreciate you pointing that out, Tim, and we'll follow up. Golly gee, yes, we do need to follow up on that. And then his second one about, we said some of the fluid escapes features of sand filled, and they are indeed, there appear to be sand volcanoes at the top. And I would say absolutely the remobilization of the sands is almost certainly with water that has come out of the clays, yes. Not that I have proof of that, but that would be a much more sensible mechanism.
Yeah. So we see flow of water up through the sand. We see flow of mud going into the sand as diapirs. We also see altered mud, where the mud has been effectively, the mud itself has changed its chemistry by the water flow. We see that material also intruding upwards into the sand. So there's a lot of different things happening.
All right, guys, we have time if there are any more questions. For now, I will share my screen to sort of re-promote this student webinar that is coming up next week. So Jill and Frank, thank you so much for joining us today. That was a really great virtual field trip. It brought a lot of sort of dynamic movement to the question and the different study sites. So I really appreciate that. And I know our SEDS Online listeners do as well. So thank you again. We loved having you. Don't forget, everybody, to join us next week for this first SEDS Online student webinar, where we'll be talking about mixed carbonate and clastic systems and different depositional processes, where we'll have 4 different PhD students and who are going to give sort of their different perspective on that topic. So yes, so in the chat, just Stephen says, thank you again, Jill and Frank, we really appreciate it. And we look forward to seeing everybody next week.